Hey everyone, and welcome. So today, we're going to dig into something really fundamental, a law of physics that honestly our brains get wrong almost all the time. I'm talking about Newton's first law of motion. And yeah, you probably think you've got it down, but I'm willing to bet your everyday intuition has been lying to you. Let's figure out why.
Okay, let me just ask you a super simple question. To keep something moving, say at a nice steady speed, do you need to keep pushing it? Think about it. Everything you've ever done, right? Pushing a shopping cart, riding a bike, your gut, your intuition is screaming, yes, of course you do.
And you know what? It totally makes sense. If you stop pushing a car, well, it stops moving. Stop pedaling your bike and you coast to a halt. It feels like our entire lives have been one big experiment proving this rule. But here's the thing. While our experience is totally real, our conclusion, it's completely wrong. We're all being tricked by this invisible force that's, well, it's always there.
And that culprit, that invisible trickster, is friction. Yep, friction. It's the force that resists motion, and it is everywhere on Earth. You slide a book across the table, what brings it to a stop? Friction. Our world is just so full of it, so saturated with friction, that we've basically built our entire understanding of how things move on a totally faulty idea.
So this universal experience, this thing we all feel, it leads us straight into what we can call the constant push myth. So to really bust this myth, we've got to get to the truth of how the universe actually works. And you could almost think of it as a law of laziness. Sounds a bit better than its real name, right? The law of inertia. But trust me, this concept is the key to all of it.
All right, so what is Newton's first law officially? Here's the textbook definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless it's acted on by an unbalanced force. Okay, that's a mouthful, I know.
But let's break that down. A much, much easier way to think about it is this. Objects just keep on doing what they're doing. Seriously, that's it. If something's just sitting there, it wants to keep sitting there. If it's moving, it wants to keep moving. Just like that. They kind of resist change.
Now, the most important part of that whole definition, the real secret sauce, is that last little bit, unless acted upon by an unbalanced force. That phrase is everything. So the big question is, what in the world does unbalanced actually mean?
Okay, take a look at this hockey puck. This diagram is perfect for explaining it. See diagram E? Imagine you have two forces pulling on that puck, but they're equal and in opposite directions. What happens? Well, they just cancel each other out, right? The net force, the overall force, is zero. So because those forces are balanced, the puck's motion doesn't change one bit. If it was sitting still, it stays still. If it was already gliding along, it just keeps on gliding at that exact same speed.
Now, let's switch over to diagram A. See the difference? Here, there's only one force pushing on the puck. There's nothing fighting against it. It's unopposed. That is an unbalanced force. And this is the only thing that can actually change an object's motion. An unbalanced force is what causes acceleration.
Okay, enough with the diagrams and textbooks. Let's talk about the real world. Because once you get this idea of inertia, I promise you, you will start seeing it absolutely everywhere, especially in, well, kind of messy situations. All right, picture this. You're in your car, you've got a fresh cup of coffee, you hit the gas a little too hard. What happens? Coffee all over your lap, right? Here's why. The car shoots forward, but the coffee is just trying to obey Newton's law. It wants to keep on doing what it was doing, which was just sitting still. So the car literally moves out from underneath the coffee, and splash, that's pure inertia. And it works the other way too. When you slam on the brakes, the car stops, but what about you? Your body wants to keep going at, say, 60 miles an hour. It will keep going until an unbalanced force stops it. And thankfully, that unbalanced force is your seatbelt and not the windshield. You can think of seatbelts as our personal inertia managers.
Oh, here's a great one. Getting that stubborn ketchup out of a glass bottle. You know the move. You swing the bottle down really fast and then stop it suddenly. Your hand provides that unbalanced force to stop the bottle. But the ketchup inside, it has no idea you stopped. It just keeps on moving, right out of the bottle and onto your fries. You're using inertia to your advantage.
Okay, last one, and maybe you've experienced this one personally. You're cruising on a skateboard, everything's great, and then a tiny little rock stops a wheel.
The skateboard stops dead in its tracks, but you? Nope. You keep on doing what you were doing. You basically become a human projectile flying forward until an unbalanced force stops you, and that's usually the pavement. Ouch. All thanks to inertia.
So, this whole constant push myth, it's not just a one-off thing. It's actually part of a bigger pattern of how we tend to mix up physics concepts. In physics, words mean very, very specific things, and it's super easy to get them tangled up.
Like, for example, we often use velocity and acceleration like they're the same thing. They're not. Velocity is just your speed and your direction. Simple. But acceleration, that's any change in your velocity. So speeding up, slowing down, even just turning a corner, that's all acceleration. Same thing with momentum and force. Momentum is kind of the amount of oomph an object has. It's motion. A force is the push or pull that's needed to change that momentum. Getting these words right is actually a huge step.
So let's bring this all together. What's the big idea here? Well, getting Newton's first law isn't just about, acing a test. It's more like putting on a new pair of glasses. It really lets you peel back this layer of everyday experience and see the fundamental rules that are running the entire universe.
And look, the problem isn't that our senses are lying to us or that we're dumb. It's just that our brains are perfectly calibrated for one very specific place, planet Earth, with all of its friction and air resistance. Newton's law just strips all that away to show you the more basic, fundamental reality that's underneath it all. The rules that govern everything from a planet in orbit to a puck on the ice. Just think back to that book we were sliding across the table. This quote just nails it. In a world without friction, that book wouldn't stop. It would just keep on sliding at the exact same speed, in the exact same direction, forever. Kind of wild to think about, right?
Okay, so this is it, the single most important takeaway. If you remember one thing from this whole explainer, let it be this. Forces don't cause motion. Things in motion are perfectly happy to stay in motion all on their own. What unbalanced forces cause is a change in motion. They cause acceleration. And that right there is the big myth we set out to bust today.
And that's pretty much a wrap. So I'll leave you with a question to chew on. Now that you have this new lens, this new way of seeing inertia, what are some things in your own life that suddenly make a whole lot more sense? Like when a magician yanks a tablecloth out from under a set of dishes? Think about it. Thanks so much for tuning in.